The C++ algorithms library defines a set of useful, reusable, and generic functions that are optimized for iterating over data ranges. It contains a number of manipulation operations that offers a lot of customization for your application. The reason I think it's so important that we start building applications using that library is because you see that it's going to be very easy to port that part of your code to run completely in parallel. And by parallel, I mean both CPU and GPU parallel. Yes, you heard it right. GPU parallelism is really easy if we start building an application with those kind of libraries already in place. And today I'll show you exactly how you can write a code that uses the STL Algorithms library that is easily portable to run in parallel in GPU or CPU. Hi, my name is Marcos and this is Practical Software. Following the paradigm of the STL, and STL stands for Standard Template Library in the C++, the algorithms library offers the possibility of applying functions over generic data. And this means in practice that this kind of algorithms, they shouldn't care how the data looks like. They care that there is a concept of a range within the data. And in principle, it can be simply a set of data points that we can just traverse through like a range. And the output of this kind of functions, it can be either another range or some kind of summarized operation over the range. So this is the concept of the algorithms library. And they provide lots of facilities for you to use in a generic way over your application. To name a few of the functions that we should expect from the algorithms library, we have sorting, searching, counting, data copy, and a few others. However, in today's video, I want to focus on two special functions that I care from the deepest parts of my heart, which are data transformation and data reduction. Let's quickly go through those two concepts. What does it mean to apply data transformation? In essence, let's say you have a data range, and a very simple implementation of this concept is a vector or an array. So you have a collection of elements that are contiguous in memory. Data transformation in essence means that we want to apply some function over an element of X, and this will yield an output. And in principle, the data transformation will produce another range with the same size. However, the elements are transformed to something else. So in this example, X0 was transformed into Y0 that way. This is the concept of data transformation that the algorithms library applies. And the other very nice one is called data reduction. And the name already suggests, let me just recopy that. Let's say I want to somehow reduce. What does this mean? In essence, it means that we're gonna do something over the entire range, and this is gonna produce, let's say, a single element. It's not gonna give me another range. It's not gonna give me part of the range. It's gonna give me a single value that in a way, in a very meaningful way, summarizes the whole input range. A very simple example is simply the sum operation. What is the sum operation? The sum operation, in that case, I just show above us. So let's call this Z. So Z is the summation of xi from 0 to n. And this means, of course, z equals to x0 plus x1 plus plus xn. Sorry about my handwriting. My parents are both doctors. This is a summation, and this is an example of data reduction. An example of data transformation is if yi equals to xi, for example, square. So for every element, we would apply a function of x that equals x squared. Of course, over all the elements, then we have a new range. You might be wondering, why the hell do I need an algorithms library to do such a thing? I could do this in a for loop. I can do this in a whatever. Well, I don't need a library for this, and I'll tell you why. The reason is, first, it's a standard. So this means that there could be several implementations over the same interface definition, which is like this data transformation. And the implementation can vary and apply the same output in a very particularly optimized way. In other words, let's say you want to compute that operation over your data range. The implementation will parallelize this operation. So it's gonna apply in a, let's say you have 8 cores in your computer. So the first core takes care of this first half, other core takes care of other half. So you can leave this detail of parallelization to the implementation, which is really nice. You shouldn't, you don't care how this works, you care that's gonna give you an output, and you can tell the implementation how you wanna do it. Should it be really fast? Should it be precise? Should I use a single core, multiple core? Should I use a GPU for that? And using standards helps vendors and suppliers do the same operation in different ways. It can be really useful and benefit your application, depending on your case. And naturally, if we want to do the reduction part and leave the implementation to help us do this in parallel, this is of course totally possible. Particularly for reduction, it's a bit more, it's a bit more complex the way you do it, but it's totally possible up to the vendor, up to the implementation that of this interface in the STL. So just to give you a little bit of the idea is in parallel, you could have one core add those two guys, and then another core add those two guys, and so on and so forth. And then in another, let's say, level of reduction, it combines the outputs of those two and the outputs of those two into another set of outputs, and then combines. And then in the final level, you have your Z value that you're waiting for the beginning. Again, really useful, really nice that we have several ways of applying the same operation in different manners, making sure that the output is more important than how we get there. But it's sometimes important that we know a little bit of how it is done, so we do it faster, most of the cases. Now, there is another special function that I really love, which is just a combination of the two things we just saw. So there is something called transform reduce in the STL, and the reason why it exists is because there is a very nice way we can perform these two steps in a way that we save a lot of memory. So in essence, we have the same, let's say, input array, or should I say input range. We want to apply some kind of fn over all the elements, and we want that output to be reduced to something. So the STL offers us a way to do those combinations in a single go. Again, we could have just done one at a time way, but imagine that case. Imagine this, you have an input data. It is 4 gigabytes of data, and you just want to transform this data to something else and then compute the average of it. So if we go one step by step, this means automatically that your output requires 4 gigabytes of data, because you have to transform the whole thing, allocate the whole memory for the storage of the output and then apply the reduction. There's a way we can do this without having to store the output, which is really nice. It's really memory efficient, and you don't pay for performance. Because, again, we can just apply the function to two elements, pair them up, apply the reduction, and have the summation reduction operation actually already computed for us. And then we can go on and further reduce until we get that final important element, resulting element that we care about. Again, the same operation is offered in STL, meaning that the suppliers can apply optimized, parallelized ways to apply this reduction for us. It's really nice. Enough theory, let's get practical. In today's video, I'll show exactly how to apply those concepts in a CPU, in a parallelized CPU, and in a GPU. Everything in one single video. Ready? Let's go. Disclaimer, again for this video, I'm gonna use Docker to once more enforce that cleanup environment and teach you in the process, maybe you learn one thing or two how to use Dockers. So let me start the image, Docker run. I'm gonna run in the background, leave it alive. Let's name it algorithms. And especially today, I'm gonna use an NVIDIA image as a base because we're gonna see some GPU processing happening. So really nice. Especially for NVIDIA containers, we do this, and I'm gonna enable all my GPUs. I'm gonna enable the container to use my GPUs. Amazing, that's it. So I can jump inside the image just like this. And here I am. I am inside the container. It's supposedly connected to my GPU. It is. So we are ready to program some fancy stuff with the GPU already. Okay, cool. Now we open Visual Studio Code, and we will use an extension to connect to that container. So if we go to Visual Studio Extensions, this is the one you need. We will use CMake. If you haven't seen CMake yet, have a look at my video. We are using the extensions of CMake and of course C++. So that this top 4 extensions are useful for today's video. All right, now we attach our code to the running container. You saw the name, it was algorithms. And now I am inside a container. What I'm gonna do is I'm gonna create I'm in the root, I'm gonna create a folder called algorithms, and I will scope my Visual Studio Code to that folder, just like that. Like the previous video, I use CMake as a C++ project manager. I'm about to install it, so apt update, apt install CMake, and build essential. We now make a CMake lists.txt. Let's call it transform. This is the name of the binary, transform. I should be able to build it, and I should be able to compile it. Build and compile the same thing. Now I'm able to run it. Perfect. Very nice. Let's use the algorithms library. All right, for the sake of simplicity, let's just use the same example I showed you earlier. So we define a vector. It could have been other types of containers. It could have been a set or a map or anything that has a range. Remember that. But let's use a vector for now. These are my inputs. Just 10 elements is enough. I'm gonna fill those guys. I'm gonna start with the 0. And I'm gonna fill those guys accordingly. So auto for every element that belongs to the range, I will assign it the starting value, and the starting value is going to be incremented by 1. Looking good. Why is it complaining? Oh yes, it should have been back here. And let me just print the elements while I fill those, just for the sake of completeness or visualizing things. Okay, so I can just make it, and I'm gonna compile it and run it. So yes, so this is our vector. It's assigned as these counting numbers. Let's first use that very nice function that I told you about, which is std transform. First argument is an input dot begin, or it could have been a pointer, and then the end could have been a pointer plus the number of elements. So the concept of range is it's quite flexible. It could have been iterators or pointers, anything that you could increment, fundamentally increment, so it points to the next element in the range. For vector ranges, this is just a pointer increasing over the span of the vector. So we could use this, or we could have done dot begin plus 10. It does also work. Let's use begin and end, and we're gonna have to store the results somewhere. So I am forced to create an output vector to store the results. Outputs. And I only have to tell what this output vector begins. And now the operation. So for simplicity, I'm going to use a lambda. It always takes the same type of the vector or of the container as an input. And you have the output has to be of the same type of the output vector. Let's just return input element times itself. I'm going to run it. Let's make and run. Looking good. Now I'm going to just print out the outputs. This is where I expect this lambda function, this is fundamental operator that iterates, that it applies to the range to work. Now I expect the square root of everything. And it worked. Oof. Yes, it worked. I know this may sound too simple, but it's important that we understand that those operations are fundamentally flexible and powerful when the implementation is tweaked a little bit to apply for this parallelism I just told you about. Well, how does this look in practice? Just like this. All you have to do is, there are a few steps, but the first one is to do this, execution, and simply add execution colon parallel or par. This is enough to instruct your compiler to run this whole bunch here in parallel. However, I am expecting a failure to happen. Yes, exactly that one. The reason this happened is because the compiler I'm using is GCC, and GCC doesn't have the implementation of a parallelism to this std transform or any algorithm operation, which is fine. So it's fair that it doesn't provide us, and it tells you which library is missing, and it's TBB. I don't know why, for some reason, GCC thought Intel TBB. It's a library from Intel. It's thread building blocks. I don't know what happened that GCC defaults to that library, but it's fine. I guess it's good enough. But we have to install it for this to work. Luckily, we are in a container, a window, non-Windows. It's a container machine. It's a Linux machine, so it's easily installable. You could have either compiled yourself the library and install to the system, or do this: apt install lib tbb dev. It's already installed. Nice. Maybe it comes with a container, or maybe I install it while trying to do this. I don't know, but it's installed. All I have to do now is to include this in the CMake as a dependency. Find package, TBB required, and now we do CMake dot dot. I think I have to do uppercase. And now I just have to link it, target. If you want to know more about CMake, go to that video I made before. Can I make it? Yes, it works. Perfect. Now, that's all. My transform is in parallel. Should I care about more details than this? Maybe. The TBB is kind of a smart library. It knows how many threads you need. For example, here we're just seeing 10 elements. It's probably not gonna use parallelism yet. However, if we had a larger range, it would use as many threads as it think it needs. Again, most of the cases, this is fine. If you have like limited resources, limited memory, and it can't do multi-threading, yeah, the thinking now is different. Like maybe you should not parallelize at all, but yeah, for the sake of simplicity, and just showing you how easy it is to make part of the code in parallel without doing much. This is how we do it. Let's say we want to apply a larger range. And I'm gonna build it. How do I know it's running in parallel? Oh, I'm gonna remove this. It's ugly. How do I know this is really running in parallel? Well, we could do some checks. If you're like me, you don't trust everything you see, you do some checks. One naive way to check is just by timing the function, because we expect that the parallel version is faster, as much faster as many cores we have. So this is roughly the estimate. This is a way to time the function. We use chrono. We compute the clock at this moment again, minus the start timer. And we take the count, the millisecond counts. Took 2 milliseconds. Let me increase. May I expect 20, 200 milliseconds. Yeah, this should be enough. Let's see how fast this is. Start, stop, 190 milliseconds. Okay, does it look like this? Yeah, so it takes a time before that to allocate a lot of memory. Then we run the function, and then we take the delta, which is reasonable. Let's remove the parallel. Let's use it in sequence. Remember this, 186, 190, so roughly 200 milliseconds. Let's see how long it takes without the parallel. That's much higher. Yeah, so we already know it's in parallel. Nice. A way to really, like, because the operation here is really simple, it's just a square number. But what if was more complex, which is really more, yeah, it's a more concrete use case. Let's say something that within the lambda is more complex. So let's emulate that by adding more fancy operations. So I'm gonna add CMath, and I will apply the cosine of the sine of the cosine. So this supposedly is gonna run much slower than just the square number, because then, yeah, we're just concatenating operations. Let's see how much it takes in a sequence call. So right now we are already iterating of this over the range of elements. Yeah, it's already taking a reasonable amount of time. That's, yeah, okay. How about in parallel? See how quickly I change the implementation detail of how this should be executed. So already feel a little bit of how easy it is. Okay, now in parallel, start, stop. Yeah, 8 times faster. Just adding this small option in the function. If the function were more complex, then we expect more change. And for reduction, it's pretty much the same. Let's say we want to add an operation that reduces the whole set. So we have a lot of elements here. It's starting from 0, 1, all the way to n, and this is n. What if we want to sum everything to a single number? Let's add all the elements. This is how we do it. std reduce. Again, we give it an input iterator, which is our input dot begin. We give it the final element, and we give it a. So here we can have a look. We give it a starting value, which is 0. Usually, it could have been something else from another operation. Start val, and we give a reduction operation. So the standard library gives us the std plus, which fundamentally calls the operator plus of this primitive. So this is cool. We could also do one ourselves, but first let's just use this. Total sum is like this, and I'm gonna print this out. And we'll remove that for a bit. And we don't need the output. We just need to summarize this. So all we need is like this. This is the final value that I spoke about. So that everything reduces to that value. It's a straightforward concept. So if I compile, this is what the sum equals. Shall we check? Maybe, but let's do it simpler. Let's say we are counting from 1 to 10. 55. So and this is actual the summation. So I trust that if we use the whole range, this is possibly likely to be the truth. Yet again, all we have to do to apply for parallelism is std execution par. So we're running the reduction in parallel as well. Okay, let's run this benchmark again. And yeah, of course, this is gonna take a very small amount of time, but I'm gonna ramp up the number of elements. All right, so yeah, I'm running parallel for that amount of elements, and it took 188 milliseconds. Let's run in sequence. How much time do you think it's gonna take? So from 188 milliseconds all the way to almost a full second. Yeah, this is data transformation, data reduction, CPU parallel, not GPU parallel, CPU parallel, and CPU sequence. We still are gonna see the GPU parallel version shortly. But before, let's have a look at the transform reduce, my favorite operation. The transform reduce, like I told you, it takes both things in the same time. Okay, let's start over. Now, I don't need an output vector. I need only the, I'm gonna get the remaining, the resulting summation value for this reduction operation. So std transform reduce, really neat function. I give a range of the inputs, begin. I give the final part of it. By the way, we can have a transformation operation that works for two set of inputs. And this is useful for optimization purposes, but mathematical optimization, not programming optimization. We're gonna talk about this maybe later, not in this video. All right, so we need also to feed this initial value. Let's call it double total sum equals 0. Total sum. We need a binary operator. So this is the operator that runs for the reduction. And I can use the standard one, std plus for doubles. Perfect. And now the transform operation. The transform operation takes the element. So this is a unary operation. It takes a single element and returns another element of the processed function. Yeah, let's give it the lambda. And now we are done. And of course, this is going to yield the final sum. I could have just overwritten the total sum, but I'm going to call it a new thing. And this is the transform. What am I missing? Oh, yes, of course I missed this. Amazing. All right. What should be the output of this reduction operation? Reduction result. And that should be enough. Well, yeah. This is probably right. So if you take 1 squared plus 2 squared plus 3 squared and plus plus 10 squared, this is the result. Fundamentally, what we're doing is applying the transformation first, then reducing it to that single value. Yeah, I'm a bit crazy about some kind of stuff, so I'm gonna check. I hope they are the same. Yes, they are. Oof. Okay, reduction works. Of course, naturally, if I want to parallelize this, it still works. All right, some final notes for this case is, of course, this could have been this. It's just a value. You don't have to define it somewhere. I defined it because usually we have some kind of functor or tuple, a special data type that we not simply initialize like this. So one of the things I want to tell about this kind of operation is, let me remove this ugly part, is that this is the transformation operation and the reduction operation both could have been functors. Functors are classes or structs that defines the operator parenthesis, and you can pass it along some other classes and they know, okay, I can call this. This is a callable thing. It's not just an object, it's a callable object, and I can pass arguments to it. It's really useful, especially if this kind of functor has some kind of state. So we're going to see more details about this later, but it's important that we know a little bit on how to write this. So what if we had a special operation? It's just a struct. If it's a functor, I have to define this. I'm gonna use it as a transform of the transform part, so it returns a double, and it takes two doubles, a single double as an input. Input element, and I'm operator, and I will store for the purpose of this functor. Let's say I want to configure the functor somehow. I'm gonna store a value called scalar. So I can initialize the functor and I can define the scalar. By the way, this notation with the underscore in the private, this is not a private one, but it could have been a private, is a Google syntax standard. I'd initialize the scalar to that value. Double, yes, okay, looking good. So we could actually, instead of returning some squares, we could return this input element times that scalar. That is programmable. So we can pass the whole class configured to some special value. And yeah, for the reduction, I'm gonna use the summation, the standard summation. And now we are configuring how the transform reduction can work. Reduction results, final sum, yeah, looking good. 55, which is expected. So we're not summing up the squares anymore. We're summing up the numbers themselves times the scalar. But I can easily configure. Let's say I want to sum everything times 2. That's how we do it. We transform first and then multiply by 2. Coincidentally, because this is a linear operation, if I times 2 all the elements to the input, I'm also timing times 2 the output. So in that case, it's straightforward. But the purpose here is that you can pass functors, and functors are powerful tools to preserve state if you need that. Now you are ready to do some GPU programming with me. Okay, let's see how this GPU thing look like. We're back in the code. We have to now instruct our build system to find the GPU facilities. Luckily for CMake, this is really simple. All we have to do is to enable language CUDA. And this is enough. So already, if I do CMake ... it's gonna look for the CUDA. It's probably whenever I call it. But it understands that instruction already and knows what to do. To compile CUDA programs, if you don't know much about CUDA, well, the primer is it's this whole tool set for developing in GPU, in NVIDIA GPUs. It offers you a special compiler that compiles code for both CPU and GPU. It's called NVCC, and it's a very handy way to program your GPU in a very generic way for general purposes. It's not like OpenGL. It's really specialized for massive computing over massive data sets. Over the scale of the multi-threading here is huge, and hence the importance of getting used to this kind of facilities in the STL Algorithms library. All right. So now, if I want to compile a program to perform CUDA compilation, meaning compile GPU functions, all we have to do is to put .cu. Of course, you have to change this to, and this should be enough to tell CMake to tell CUDA, hey, compile this as a CUDA program. And voila, it works. And it gives us the same results. It's pretty much for CPU programming, like we just did here, it's pretty much the same thing. But we can pull in CUDA programming. There is a very special library in the CUDA toolset called Trust. The Trust is a CUDA attempt to close the gap between the STL from C++ to CUDA programming. So I'm going to use it for sure to demonstrate this STL way of working and programming. So, but before, I'm going to use some autocompletion. Okay, now I should see all the include folders that my project depends on, including the TBB. TBB, yes, it's here. So that library is called Trust. It comes with the CUDA, so if you just do this, it's already coming together. And this CUDA allows us to do the transform, for example. I think it's just transform. Yeah, we can do the reduce, and just checking. Thrust, transform, yes. Reduce, yes. And where is transform, reduce together? Oh, there it is. Yes, it's another header file. Okay, so Thrust is this very nice library. It helps us program in the GPU in a generic way. And we use its first structure to put data into the GPU. It is the device vector. And I'm gonna comment this for now. I'm gonna copy this data structure of this range into a CUDA memory, GPU memory. So I initialize the vector, Thrust vector. It's just some doubles. Device input. It has the same number of elements, so I can tell the library to already allocate those guys. And I can have thrust copy. And I can copy from my host device into my... It works. So how do I know it works? I can print out this device vector into some elements, let's say in the 5th position. And it should give me 4 or 6. Yeah, that's 6. Yeah, because this is, 0 index, whatever. Yeah, this is 6, which is nice. Okay, let's do the actual fun stuff, which is running those generalized functions over the GPU. First things first, you always have to copy data from the host to the GPU. There's no way around it, and this is somewhat an expensive operation. It's really fast, really fast, but depending on the machine, on your hardware specification, it can take some time. So the way of working, the advised way of working is to really put all the data you must put in the GPU and keep it in there as much as you can. In other words, try to use the GPU as much as you can without as much memory copies. All right, enough of this. Let's do some reduction. All right, the way, let's apply this very same function, transform reduce, over the same data set, but in the GPU. Luckily, there's this facility here, transform reduce, and instead of giving host or CPU pointers, we give GPU pointers, and we have one, this one. I forgot to copy the elements. I shouldn't have erased this. Thrust, transform reduce, give it a pointer from the device, give it the device finish line of the data, yes, initial value. Why is it taking? Oh no, this one for some reason takes the transform operation first, which is fine. But this is the magic. So I'm gonna reuse that guy simply by putting device. So I compile this in the GPU, and I'm also compiling in the host. So it works just like this. This is the transform operation, just 2. And the reduction operation, before the reduction, I give it the first value, 0. And finally, the binary operation that combines 2 of those into the single one. I believe thrust also gives us plus, yes. So this is, in other words, a definition of the operation plus for doubles, but it is already compiled in the CPU, in the GPU. Maybe this works already. Auto result. And it is supposedly the same. So 110 is the one I'm expecting. It's correct. Really nice. Okay, how fast is this comparing to the CPU processing? We can check. Let's increase the scale here. 10,000. How much is this? 10,000, a million. 10 million, 100 million. Yeah, okay. This is not very important for the video. I'm gonna just skip that part because this is really just already using all the stuff we learned, but just putting them together. So skip. Okay, this is me from the future. I just wrote some not very interesting code. So we profile what is happening. We can quickly go through it. So first, there is some CUDA profiling of things happening here. I'm profiling how much time it takes to copy all the memory, just for the sake of knowing. Then I profile the actual transform reduce operation. Then we run a sequential transform reduce from STL. over the CPU, and finally another transform reduce from the from the CPU, but in parallel. Yeah, looking good. I print out the times and I print out the results. Now, not to be entirely unfair with the CPU, I'm gonna build with the compilation flag that instructs the compiler, the build system to use optimization flags. Else, it's gonna compile in the debug mode, and it's likely to be much slower than it could have been. So this is how we do it. The build is not it. It's make build type equals release type. Something is missing always. Okay, amazing. Now we can compile it. So, yeah, like I said, memory copy takes a time, but look at that. The actual runtime for performing the reduce operation was 0.009. It was almost 2 orders of magnitude faster than a single CPU execution. For a parallel execution, it was still orders of magnitude faster. So look at that. So the parallel wasn't very optimized comparing the CPU. For there could be many reasons for it. Maybe the operation is too simplistic. Actually, this is the case. So the time it takes for the CPU to set up all those threads to run a very simple operation, maybe it's not that nice. If we use that sine, cosine, and sine again, just to make it a little bit more complex, and of course, the GPU has implementation for those, maybe we're gonna see something more interesting. So now we're gonna use more complex operations over the elements and expect that the ranges are much different. So now the GPU it took much more time because those are supposedly more complex operations. The CPU is still running 11 seconds and then the parallel took its time. It's much more fair to do like this. And look at the results, they're the same as expected, but this is more a fair comparison. So this is how fast the GPU was. Again, 2 orders of magnitude, almost, regarding the CPU, single execution CPU. And the parallel CPU was 1 order faster than the single execution one. Now this is much more reasonable. But yeah, you see that I'm using the same functor. I just had to do this, the device and host. And this was as easy as calling that function with the same, almost the same parameters for all the cases. And that's it for the video. I hope you had learned something. I think it's really useful to have this knowledge, especially if you are in some kind of high performance requirements for your applications or projects. And this is the case for my hobby projects as well. I have to compute stuff really fast in real time, and this kind of stuff, it proved itself to be extremely useful. So I hope you liked it, and we talk soon. Bye.